A couple things before I start. One, I want to thank Apex for hosting this. It's been really good for me. I haven't been to a lot of conferences like maybe some of you, and it's like, oh yeah, sometimes my brain needs to get turned on in a little different way than I'm used to. So I appreciate that. I want to acknowledge that this was work that I'm presenting, but only because Louis didn't want to present twice. Um, and so it's really a collaboration, and in this one in particular, between the TNC team here in Nevada, not here in Nevada, but in Nevada, as well as Apex. So there were kind of three main goals here, and one that I don't want to put up on a screen, but I'll tell you. So the first one was to develop a new non-native annual species map at a higher resolution than what we can generally get for really large areas. In Great Basin, kind of the Intermountain West, invasive non-natives are kind of one of our major problem. And so they're really a concern and a restoration focus. So that's an important piece as we go through. The next thing that we wanted to do was estimate carbon dynamics of management. So looking at no management and management scenario to see how those differ at three different landscapes. And a landscape here is like 400,000 acres, so that we could understand the dynamics there to then do our third one, which is scale up the potential for how much carbon can be restored, how much carbon can be sequestered using management and mostly restoration techniques from converting non-native annual invasive species dominated spot to something that's more in line with other natural resource management objectives. And I'll say a fourth one that wasn't on here is how do we do all this on a relatively small budget? We didn't have as big of a budget as we had planned when we had first proposed, so we had to make some assumptions and cut corners in places in order to kind of do this. And I think we'll all appreciate how a project starts in one place and goes in another place because of real world constraints. So how did we make our map? This is a work that Sarah, she was the one that really spearheaded all this. Again, we wanted a higher resolution than what was generally available to us. Also a freer version of the data. For a lot of our landscapes that we do, as I've been talking to folks, we use 1.5 meter resolution. That's super resolved. It's also pretty expensive to get and then to classify. So we were looking to go a little bit bigger, and we settled on Sentinel-2, which is a relatively new satellite. It's 10 meters. It's available via Google Earth Engine. It only goes back to 2017, but it has about a 5-day pass. So it fits a lot of the criteria for mapping the phenology of non-native annuals, which is often pretty different than the phenology of the native species in these areas. So Sarah used a random forest builder. And in that, we use a couple different data sources. One was the BLM AIM data, which I didn't know, Jim, about the fuzzy location, so now I'm a little worried, but I think our map was good. So anyway, I did always trust Sarah. That's what I've learned. The other thing that we've used is because we've mapped these areas at 1.5 meters for those three landscapes, and because we do extensive ground truthing in those ones, we use those as training and validation data sets as well. And this will get us to a map of annual estimates of cover for these non-native annual grasses and forbs that we threw in there, because sometimes you can't really tell those two apart. So this is kind of the results of goal one. Over here on this chart on the left, what you're seeing is the kind of the most important variable, explanatory variables, in order to kind of pull out these things. And you can see that elevation was really, really important. Cheatgrass, which is the main driver in most of Nevada, has some elevational limits. And those other ones are just derived products from the satellite imagery. Mostly, Sarah can throw a pen if I'm wrong on that one. And then you can see the output of our in our study area in kind of a binned of a bin case. Again, the species change a little bit, but as you go from kind of north to south, but you can start to see where our problem areas potentially are. One of the things that we've also done is kind of compared this at a kind of casual way to other maps that are similar at least in process. So on the left, you see our 10-meter resolution. In the center is a 250-meter resolution. It's called the near real-time annual grass estimate or something. The near real-time is right. Everything else I forget. And then the last one is that's from the RC map project. And so you can see that generally we do a fairly good job of agreeing with these things. In some cases, it looks like we may be picking up on some things that other folks have not, these other products are not able to pick up. Also, because of the timeframes of ours, I think we can pick up on some of the fires and things that, again, that the other folks weren't able to pick up. So we have this map. Awesome, cool. Now what we need to do is figure out the carbon dynamics on the landscape. So we had previously mapped these are all kind of based around 3 previous projects. One in the kind of South Columbian Plateau, that's the IL. One in Central Nevada, or the Central Basin and Range. That's the we call that the ST Horseshoe. It's a place around a ranch. And then we have Pine Valley Mountain Home, which is in Utah, which has it's in the Great Basin, but it has more of a monsoonal characteristic to it, and that's actually going to be important when it comes to looking at our results. So those were all previously mapped. Those were all previously modeled. So we had a lot of our model building was already done. And so what we needed to do is just tweak the inputs that we want to focus on the particular aspects of ecological change that we wanted to focus on. We combined those models in STSIM with STSIM stock and flow package, and we used Lucas inputs for that. And you can generally see a snapshot of our stocks and flows. I would say the aquatic, the hardwood extracted, the green/ag, and the straw were all ones that we actually didn't worry about, because we're focused on rangelands here. We're focused on restoration, and those, for those of you who have driven across Nevada, we don't have a lot of grain ag, and we don't have a lot of hardwood extraction in most of the places. So we didn't worry too much about that. And again, I want to say this particular part, Leonardo and Shri, when he was still with Apex, helped us a lot with implementing this piece. So in order to kind of look at, well, what does restoration potentially can do, we created 2 scenarios. These were fairly simplistic scenarios compared to some of our other scenarios that we do for modeling. We had what we called a custodial, and we, as Louis likes to say, that we used to call this kind of thing a minimum management, but we are having some management in there. Grazing is still occurring on these landscapes, and we don't model fire suppression, but we model the effects of fire suppression. So we essentially input the natural range of variability fire dynamics, but we've realized that very few places actually allow those fire dynamics to occur naturally. And so what we do is we reduce the fire rate by about 90%, because that's generally the success of suppression in terms of putting out all fires when you look across the data set. So that's our kind of baseline scenario. And then we have our seeding scenario. So it includes everything that was in the above scenario, but then we added in this kind of trying to restore these non-native sites. So seeding only occurred in sites that are dominated by non-native grasses. This matches real-world management practices. We're often with our partners, in particular with our BLM and federal partners, if there is any existing perennial or any existing shrub cover, they're often really reluctant to remove that to try to get at the cheatgrass to then re-put things in. So if it's a mix of cheatgrass and perennial, they tend to stay away from those sites from a management perspective. Annually, there was between 6,000 and 20,000 hectares of seeding that was allowed on this landscape. Each scenario and landscape was run for 30 years, but it's important to know that we did a little bit of a spit up time in the first 5 years, and then we didn't do any seeding in the last 5 years because we don't have that much water, so it takes a long time for a seeding restoration to kind of mature, and so the last 5 years are kind of, it just speeds it up because we don't have to worry about it because we're not going to account for it anyway and its impacts. You can see the list of our treatments, and if you look at the paper and like, what did you do there? We can walk through it some other time about what exactly all those mean. You can also see that we have different prices depending on where you are, and that reflected, again, our partner inputs on those. Again, We wanted to try to actually cost this stuff out and even go from a bigger landscape, but you know, I want to caution that these numbers are not hardwired somewhere, and those are going to change year to year, place to place. So what did what I'm calling the landscape level carbon dynamics, what did we see? One of the things that I think often gets overlooked in the carbon discussions and rangelands is just how much of the carbon goes down into the soil. And from a carbon sequestration perspective, I don't need to tell a lot of folk here, that's really important because that tends to be a more stable pool than the above ground, in particular if in a fire-prone system. We found that generally the Pine Valley Mountain Home site had a much higher potential for carbon sequestration via restoration than the other ones. Also, because of the costs in Utah, it was a lot cheaper. So the amount of carbon you were able to store per unit area was a lot less in this kind of monsoonal landscape than it was in some of our other landscapes. You can see the difference. So I'm just showing here what was the change in net biome productivity between that seeding scenario and that custodial. So this is the change. All three of them showed an improvement, but you can see that the one in Utah clearly improved a little bit better. The next step was taking this next part bigger up, and this was not to diminish the work, but it's a little bit of a glorified GIS exercise. And so here we're combining those first two pieces. Where are the areas of cheatgrass of non-natives that we can restore, and how do those carbon dynamics from those three example landscapes play into that? So one of the things that we wanted to do was be a little bit conservative about what we think can realistically be restored. And so we looked at cover, annual grass cover as part of that, but then we also constrained it by slope and ownership as a way to help reduce that, because not all lands can receive treatment. One of the things that I should say about all of this is that it really matters where you are and what technique you're using in terms of seeding success, and we'll talk a little bit about that later. But we're estimating this based off of the realized rates of change, and not the inputted in the model. So not just the base probability, but how do those play out given climate, given all the other things that are going on. So again, here are kind of three areas based off of those three different landscapes. So this monsoonal, the kind of central Nevada, Central Basin, and the South Columbia Plateau. And so we can see, largely because it looked like the Pine Valley Mountain Home was really successful at sequestering carbon, even though it's not our biggest area of available treatment, it did have the biggest increase in carbon, followed by those other ones. So what's going on here? Well, again, Pine Valley Mountain Home had higher success. Some of that is because it's a more productive system. Some of that is because of the management strategies that are used in Utah generally lead to higher seeding success than what we would expect in Nevada. So real world decisions and real world site conditions are really going to impact this sequestration ability. We do think that we underestimated our carbon potential because of that shoestring budget, and that's why I bring this up. We kind of used some old methodology for our modeling for the two Nevada sites, and I think if we would have had our more free reign, we probably would have updated some things, and we think that might have changed the picture. Would it have changed the overall picture? Maybe not, but we think that those numbers would certainly change a little bit. Another thing, and this will kind of come in a second too, is that right now we don't have, based off the inputs that we had, there's no difference in a cheatgrass site and a newly restored site in terms of carbon. Colin and I were having a discussion, like, does it matter? And the real thing is, we don't know. If it does matter, then we're likely really underestimating how much carbon is being sequestered. If it doesn't matter, well, then it doesn't matter, and we can just keep those two things the same. So just a couple things. One of the things I want to advocate for is that we need more carbon data in these places that we think don't matter for carbon. If you are being asked to store carbon, but you live in the Intermountain West, good luck finding the data that you need to really parameterize your models. But it's also that is like, why can't the Intermountain West contribute to this? We might not be able to contribute at the same per unit area, but we actually have a lot of area that can be restored and is also in public land, which is very different economic pressures than if it's in private land. So that's just my little like soapbox. I'm off my soapbox now. Wet meadows is another really big area, very ecologically important. There might be co-benefits to managing there. We don't know anything about the carbon dynamics there. Another thing that we ignored is the PJ dynamics. Pinyon and juniper are expanding in a lot of these places on these shrub sites. There's a lot of carbon implications for that, and we just chose to ignore that for this particular study. But that is something that I think to get a more fuller picture, you'd want to take a look at. I do think this work shows some potential for highlighting where we need data and also multi-benefits of thinking about how do we restore these lands and what are the carbon consequences. For a lot of our partners that we work with on the private side, I can't come to them and say, hey, do you want to work on a project to restore carbon? But I can come to them and say, hey, do you want to work on a project where I increase maybe your hunting, I increase habitat, which is going to get you more hunters on your landscape, or increase your forage. But if I know that there's also a carbon benefit, I can look for funding in other places. That opens the door. So understanding where those things intersect is really important in the work. So with that, I want to thank you. This is a QR for the paper that was published in Rangelands that summarizes all this stuff. So thank you.